called generated. What is it? We know what we do with it. It's just the flow of free electrons. That's all it is. And we know we'd probably want to use things like metal to do that, not things that are insulating. You remember Ohm's law from Science 9? V is IR. And if you want, you can do it like some of you guys wanted to do with V, D, and T. Okay? V is I times R, I is V over R, R is V over I. Okay? But I hope we can all do that without this funny little triangle. So what are these three things? I just showed you in a video an explanation of voltage and current. Voltage in volts is the unit we call it, and 1 volt is 1 joule per coulomb, the amount of energy per charge. Okay, just looking at the letters, that's what you get. It's the confusing one. It's like a pushing of, that says electrons. Okay? Potential difference is another way of saying voltage, or just potential. It's also called this, EMF, electromotive force, which kind of is synonymous with a pushing. Okay, so it's a little hard to explain and understand, but that's what it is. Current. It's in amps. It's also the letter I in here. Maybe we better do that. V is voltage. That's the one that's easy to understand. I is current. I guess it comes from Latin. Okay. I don't know. Didn't look it up. 1 amp is 1 coulomb per second. So that says coulombs are charge. We know that from last chapter. That's the amount of charge per second. It's like a flow. Net charge per unit of time, but we usually just leave it in seconds. Why convert it to anything else? So anything per unit time, like kilometers per unit time, we would call that a speed, right? A rate of speed. This is a rate of flow, or a flow rate of charge. Just like the analogy you saw in the video, water. It kind of makes sense. And we call water current too. We even use the same word there, don't we? Okay, so if that is current, 1 charge per second, we can have a formula here. Current is charge per unit time. You guys know Q from the last chapter? So there's a little formula. I is Q over T. Where that's charge, and we know T stands for time. Okay? And then the last thing here is R, or you guys know what that is? That's something easy to understand, resistance. Okay? It's a material, even the wire itself, resisting flow. Let's put flow of charge. What do we use in our houses these days? Copper or aluminum? We use both. Okay? Aluminum is cheaper than copper right now. The price is it's a commodity. They go up and down, just like stocks, just like gold, just like coffee, soybeans, pork bellies. Okay? Everything's traded. Orange juice. It goes up and down. And a time ago, we used to predominantly just use copper. And then they used aluminum because it was cheaper in the 70s and the 80s. And they found some problems. Now, aluminum in itself isn't a problem, but when you try to mix it with copper and do it improperly, it could cause a fire. So some insurance companies, if you got too much aluminum, they don't even want to insure you, your house, if it burns down. Because people don't do things properly. They buy fixtures like lights that say copper only, right on there, and they connect it to their aluminum wire, and as electricity goes by it, it gives and takes, heats up a bit. Aluminum will heat up a bit more than copper, and it comes loose, and next thing you know, it gets an arc, and arcs cause fires. But if you're calling BC Hydro and they're connecting the power to your house using this big fat 200 amp cable, it's aluminum. So it actually is a bit of both. Okay? But both these materials have a low resistance. We want to use them both. We don't want to use something that has a lot of resistance, which doesn't make any sense, right? So your light bulb is another word for your resistor. Okay? It absorbs all the voltage that goes through it. That's why it burns, hopefully brightly, but it's another word for a resistor. It does resist the flow of charge. It sucks it up. Okay, so let's look at a circuit. You've got a couple in front of you. And we normally would have a battery. Okay, there's a positive end and there's a negative end. They're normally cylindrical, but you know your 9 volts are boxes, rectangular prisms. So what is electricity? The flow of electrons. Guess where the electrons are, the plus and the minus? Make sense? So naturally we would take the flow of current to go in that direction. So electrons do travel from negative to positive. And once this whole abundance of electrons that we have there has dissipated, then the battery is now dead. There's no more potential difference in this battery. It doesn't do you any good. Why then do we say the flow of current goes the opposite direction? Because they made a mistake a long time ago and it just stuck. So we still do it. We still use it that way. I know. That's what it is. So in a circuit, we don't draw a battery. We just do this. Okay, that's my positive. That's the bigger one. Negative, that's the little one. When you get pictures, it won't even have that. You got to know that's the positive and that's the negative, because you're going to need to know the flow of electron. That's the symbol for a resistor. Okay, so which way does the electrons flow? That way. So I, little I, standing for the current flow, goes the other way. Okay? It's backwards. So there's your resistor. It's a light bulb. It's a bell. It's a buzzer. It's something that, it's your cell phone getting charged, okay? Something that consumes electricity. If I want to measure this, I would use what we'd show you right here. It's called a multimeter. It means it's a meter of several things. It meters voltage. It meters current. It can also meter resistance. How would I measure the voltage of this thing? I would put a voltmeter like that. Now you don't know this word yet, but that's called in parallel. It could tell me the voltage dissipated by this resistor. Or I could connect a voltmeter across the battery and find the potential difference of the battery. With any luck, it'll be the same amount that they advertise on the side of the battery. Okay? So that is a voltmeter. We measure the voltage, of course. Ammeter measures current. Where would I put an ammeter? I put it, it's called in series. These names ring a bell? You do this in Science 9? Okay, and that's a picture on a circuit diagram of an ammeter. They're in series. Now think of, this is the simplest circuit as we can get. I got a battery, I got a light bulb, just kind of like what you have there in front of you. If current is described as the flow, like flow of water, what are your possibilities? First, it goes in this direction, that's the current flow. Does it go anywhere else except through this resistor? Think of it as a big pipe. And I got a pump here, and it pumps it around. Maybe it goes to your, heat something in your house, comes back to the pump after it loses its heat. Does it matter where I put this ammeter to measure the flow of that water? Is here going to give me the same value? Yeah. Is here going to give me the same value? Here, here? It doesn't matter where I put that. There's only one path for that current to go. Okay? Series. In line. Parallel is not in line. Okay? This is not a path. I'm just putting my voltmeter there. Okay? See the difference between series and parallel? We'll talk more about it, but might as well say it now. Okay? So again, let's emphasize this. Conventional current is opposite to flow of electrons. Okay, just because, like I said, we kind of made a mistake and now it's stuck, and we wouldn't want to reprint all our old textbooks now, would we? Okay, so circuit, let's actually pause it right there. Example. A toaster. You guys toasted over a campfire? It's a lot more difficult than it seems, isn't it? Yeah. They make little gadgets to do that, like little stands and stuff, and then, but how do you get a consistent fire? Like, what's the consistent distance? Usually it just dries it out before it actually browns it. Like, it's a lot more difficult than you think. Guys, okay, a North American outlet, what does that mean? How much voltage do we got here? Yeah, 110 to 120, 115, okay? It's not exact, and it depends what other stuff's connected to it. It depends what your neighbor's doing with his appliances. But it's approximately, well, let's write it. 100, not 100, hopefully not that low. 110-ish to 120-ish. And sometimes it's not. and your appliances actually get damaged. You wonder why you fried that little circuit board in your laundry one day? You had a brownout. Now, good luck trying to prove it that it was because of a brownout and it was a hydro, because they should be responsible for that and pay for your appliances. But not many people have the means to actually prove that. And it draws 4 amps. That's the wording we usually use. For 30 seconds. A. What is the resistance of the toaster? B. How many electrons have flowed through the circuit? What's voltage in Europe, Meryl? Yeah. They also use a frequency of 50 hertz. Here we use 60 hertz for frequency. So those of you in Math 12, you're looking at a sine wave, okay? 60 hertz. 60 times per second, that wave alternates back and forth. In Europe, it's 50. They just do something different. But try to take your appliances here and plug them in over there. No good. Vice versa. You need different ones. Some people travel a lot, get hair dryers that are actually got dual voltage. You can actually flip a switch and they'll work in both places in the world when you go back and forth. Because, I mean, who wants to have 2 hair dryers, right, Colin? Okay, what's the resistance? V is I, R. Do I know I? Yes, it's 4. Do I know V? Yeah, it's 115. So R is V over I, which is 115 over 4, which is 28.8. Did I show you the symbol for an ohm? I can't remember. Is that in the notes? No? Resistance, material. I didn't. It's in ohms. Symbol, Greek letter, omega. I don't think I did that. Okay, so 28.8 ohms. That's easy. B, how many electrons have flowed through the circuit? And I know it's the opposite direction to current, but so what? What do I know? I know Q is IT, because I is Q over T. So how much charge has gone through? Well, I is 4, and what's the time? 30 seconds. So I know the amount of charge is 120. What's the units for charge? Coulombs. Great, so it's 120 coulombs, but that doesn't tell me how many electrons it is. What's the charge on 1 electron? Yeah, 1.6 times 10 to the minus 19 coulombs. I got 120 coulombs. I know it's a negative, but I'm just looking for the number of electrons. So what do? Each one's got a charge of that. I got that. So as a formula, which isn't on your formula sheet, but if you want to put it, feel free. So that's the number of electrons, right? That's charge. And that is charge of 1 electron. Okay, so I know Q is 120. I want to solve this thing for N. So some of you maybe already kind of figured that's what I'm going to do in my head. I mean, it's got to be a lot of electrons, right? So take the big number over the tiny number and do that, and you get, because the speed of light's pretty fast, isn't it? 30 seconds. Yeah, 7.5 times 10 to the 20 electrons in 30 seconds. That's how many electrons it takes to brown your toast. So do first handout, intro to current, and current 1, which is attached to it. We can do 1, 3, 4, 6 to 12. Basically, we just, the ones that say power kind of skip for now. I'll do that tomorrow. And we'll be done that tomorrow. You get a new sheet next day.